Today's lesson is 1.3 Function Families. Today we're going to talk about uh, six of our main function families, their parent function, what their graph of their parent function looks like, and some of their characteristics. Let's go ahead and get started with our linear functions. The parent function for our linears is y equals x. The graph of this function will go through the origin and will appear to be a straight line. Okay, it will always be orientated in this direction. Some characteristics about my linear function is that we oftentimes see it written in the slope-intercept form, which is, of course, y equals mx plus b, where m is our slope and b is our y-intercept. Hence the name slope-intercept form. Now remember, to do the slope, you would just go your rise over your run, and then this right here would be my y-intercept, where the graph is touching the y-axis. We also have something called the point slope form. This one, if you can guess, contains a point and the slope. You might have seen it. Let me go ahead, raise that up. Y minus y1 equals m times x minus x1, where of course, once again, m is the slope and x1 comma y1 is my point on the graph. It's just an ordered pair on the graph. All right, let's go on to the next function family, which is my quadratic function family. The parent function for this graph would be y equals x squared. The graph of this function would look something like this. Oh, almost. Hold on. Let me see. It went too much on me. Let me see. There we go. Oh, it keeps pulling up too much. It's got to go right through the origin. I can't get it to stop going up too much. So here we go. We'll just do the best we can. Something like that. I could graph it a little better, I guess. Maybe let me graph it. That might be better. So it's going to have a point right here, and then it's going to mirror itself from side to side. 3 squared is 9. Oops, I messed up on that one. Let me move that one. I wanted -2, -4. There we go. And it would look something like this. Let me see if I can connect those together and make it look better. There we go. That's better. There's our quadratic parent function. It is called a parabola. I'm going to spell it wrong. There we go. It's called a parabola. It has a vertex. Which happens to be a max or a min, depending on the orientation of your parabola. The vertex for this one would be right here. This would be considered my vertex. Okay, and it also has what is called an axis of symmetry. What's happening on the left side of the graph is the same as what's happening on the right side of the graph. Right through the vertex is our axis of symmetry, so that the point 1, 1 is mirrored on the other side at -1, +1. The point 2, 4 is mirrored at -2, 4, and the point 3, 9 is mirrored at -3, 9, because they're the same distance away from this axis of symmetry. A lot of times you see the axis of symmetry written like this, capital A, lowercase o, capital S. It's one way that we like to write the axis of symmetry. All right, our next quadratic function family are the cubic functions. These functions' parent function looks like y equals x squared, or sorry, no, we already did the squared, x cubed. And let me see, I don't know, but let me see. It should look something like this, the parent function's graph. No, it's not gonna. I'll do the best I can. There we go. Something like this. It's gonna curve a little bit through the origin there. Let me see. I think I can make that a little bit better. It's a little bit more of a curve. There we go. That looks better. Some characteristics of this graph. It does not, does not contain negative or fractional exponents. There's other graphs that do. It has what is called a rotational symmetry. At the origin, which remember is the ordered pair 0, 0. So it has a rotational symmetry. If you look right here from the origin, it's going to rotate the same in both sides. So the symmetry is the same. All right, our next function family are our cubic roots. Our cube root function. Our cube root functions, let me make sure I'm looking at the right one, have the parent function y equals, then you're going to see a radical sign with the x value in variable inside, but there's going to be a 3 here in our root. This is the cube root parent function. Okay, this parent function looks very similar to the one we just saw, but let me see if I can do the graph. It's going to do something like this. So very similar, notice, it's just kind of switched around a little bit. All right, some characteristics of this one. Let's talk about the domain and the range. So the domain and range include all positive and negative. That's my symbol for real numbers. All positive and negative real numbers. It once again has rotational, not rational, rotational symmetry at the origin, which is again the ordered pair 0, 0. So you can kind of see it here, right? The rotation here, the symmetry here to here is the same, but it's a rotational one. So we don't really have an axis of symmetry. All right, the next one is our square root functions. Our square root functions parent function is y equals, we see the radical symbol once again, an x. Now, we do not see a number in the radical. We do not see a number right here because with the square root, we all have agreed many, many years ago that the index of this radical is 2. So we never put it. We just, when we see a square root sign like that, we know that the index is 2. With the last one, we had to put the index in there because we needed to talk about the cubic root. All right, the parent function for this one looks something like this. Okay, kind of starts at the origin and goes off to infinity towards the right side of my graph. Some characteristics about this function. Oh, no, let me change my pen color. There we go. The domain and range is are limited. I guess I should put are limited to my real numbers greater than or equal to 0. Okay, we can't have any negatives. We cannot do a negative square root. You can try, but we're going to learn later in the course that when we have a negative square root, we end up with what are called imaginary numbers. And so they're just not there. So we're sticking to real numbers greater than or equal to 0. All right, it is defined as the principal, the main principal root. And we always have positive roots. We can never put a negative number underneath that square root. All right, the last function family that we're going to talk about in Algebra 2 are the absolute value functions. The parent function for the absolute value is y equals the absolute value of x. Okay, these are not the number ones. These are this is the absolute value sign. Um, we're going to talk about the absolute value in just a minute. We'll talk about it in its characteristics. But the absolute value function makes a line heading this way and makes a line heading this way. Where the quadratic graph, the parabola, looks like the letter U, the absolute value function looks like the letter V. Okay, it comes down to more of a precise point. And then let's go ahead and talk about the characteristics. Okay, so just some things to remember. The absolute value, there we go, value is the distance from zero. From zero, that number right there, a number is. Now, remember from geometry, distance, my good buddy distance, cannot be negative. So whatever number I put into the absolute value, +3, it comes out positive. If I throw in -3, it's going to come out +3. No matter what I throw in there, -5 is 5. 7 is 7. Okay, it doesn't change the sign. It does not change the sign. It only changes the sign if it's negative when it goes in, because whatever's in there needs to become positive. That's what these absolute value brackets do. Okay, so I end up with -20. My answer is 20. Okay, I'm 20 spaces from 0 in my on my that my number's 20 spaces from 0. Okay, the graph itself has a vertex. And once again, depending on the orientation, it can be a maximum or it can be a minimum. It can be a max or a min, depending. And you've probably already guessed, but this point right here would be considered my vertex, just like in the quadratic. And just like the quadratic, the last thing I want to talk about is that the absolute value does have a line of symmetry. I don't know why they don't call it an axis of symmetry because it pretty much does the same thing. It goes right through here, and your points are going to be the same distance away, right? 1 to 1. Everybody's going to match up.